welcome, and today I'm going to be going through some basic SHM questions from an exam paper to sort of explain how you can use the basic SHM knowledge that you can use to answer questions for exams. So this is just a set of exam questions that I've picked that just have some really basic sort of SHM or simple harmonic motion sort of questions. And the first question is probably one of the most popular and the most ones that I see a lot of, and it's define simple harmonic motion. So the definition of simple harmonic motion, or a system that's going under simple harmonic motion, is that acceleration is directly proportional to displacement in the negative direction. And what that means is that if something is going into simple harmonic motion, so for example, a pendulum, so if I grab a pendulum up here, so when it's displaced from its equilibrium point, so there's its displacement, it will want to accelerate back sort of towards that equilibrium point. So you have displaced it away from the equilibrium, but it will want to accelerate back. Now this is, as you can see here, a 2 marker of a question, okay? And the 2 marks available for this are one for knowing this here and this negative direction here. You could also get away with A is proportional to minus X and explain what each one of those is. So you can explain what A and X is. So I'm just looking at the mark scheme now. So they are happy with, so when a body performs under a solitary motion, the acceleration is proportional to displacement from a fixed point and always towards that fixed point. That's one way of saying it. The other one, of course, is in the negative direction. So this one here, for a body of an undamped, and this is an important term because we will be dealing with, you do deal with damping much later on, okay? So the thing here, so it's an undamped simple harmonic motion. It wants the displacement and the velocity and the acceleration with variation of time. So for AQA, we start displacement. It's always in this nice sort of cos thing here. So this is the best I can draw. I am drawing on a tablet, okay? So we've got a nice cos displacement graph here because to, of course, start the SHM, you have to move it away from the central point. So this point here, of course, is the equilibrium point. Velocity, if I go down, so velocity of is the gradient of a displacement time graph. So what I normally like to do is, one of the things I'd like to do when I'm insert, and I want to insert a shape, and I want to insert a line, is I like actually drawing lines on my exam paper. So I'm just going to zoom out for a few seconds and show you what I would do in an exam. So in an exam, I tend to like drawing lines going, if I'm ever asked to do this kind of thing for SHM or for magnetic fields, I like drawing lines. And what I do is I draw the lines of where the peaks are, the troughs are, and of course the parts where you cross zero are. And that's what I tend to do. I get a ruler and I'll draw all the way down on these exam questions so that I can see this for later on, okay? So this is just me helping myself a bit later. As you can see, my graph was a little bit naff. It wasn't brilliant, but it's the best I can do. So velocity, of course, is the gradient of that graph. So velocity is the gradient of a displacement time graph. So at this position here at the start, I've got a 0 gradient. So it'll be here. This part here is the maximum point where it is negative. I've got 0 gradient there. This one, of course, is maximum positive. This one is 0, this one is maximum negative, and this one is positive. And you've ended up with this nice sine graph, as best as I can draw on one of these, okay? So I've got a nice sine graph there. So this is a minus sine graph. And lastly, acceleration, of course, is the gradient of a velocity time graph. So here my gradient is maximum negative, then it's 0, then it's positive, then it's 0, then it's negative, then it's 0, and then it's positive again. And you get this, best as I can draw. So this is a minus cos graph. So to get to each one of these, it's the gradient of these graphs, okay? And as you can see, these lines that I drew are really, really useful. So this whole question is actually worth 5 marks. It's quite a really heavy question. And the kind of marks you get are basically for the actual drawing itself. So you get 1 mark for each of the, well, there we go. You get 1 mark for each of the graphs being correct. So that's 3 marks in total. So 1, 2, 3. Okay, you get 1 mark for just generally knowing the shape should be sinusoidal, and then you also get 1 mark for, of course, getting the signs the right way around. So the signs is the 2nd mark here, which is quite good. So it's a 5-mark question. It's a really, really nice question to use. So if you want to in an exam, just draw these lines down. The examiner will not mark you down for having these dotty lines. Normally I would draw them in a dotty line, but I've drawn them in a different colour here, just to help guide me draw these actual graphs. Okay, so that's just the first question, a very basics of SHM. So this is question 2. So the graph below illustrates the displacement time of a body that performs SHM. Determine the following quantities. So from this actual determine the quantities or the values of these objects. So the amplitude of the motion. So the amplitude is the displacement, the maximum displacement from the actual object, the actual equilibrium point. So again, this graph here, we got the equilibrium point here. So the whole thing from peak to peak is, from peak to trough is 5 centimeters. So I know in total, if it was going to go from one position to the other position of a swing, so if I had, for example, there's my equilibrium point, I've got a position here, I know the position there, I know this is going to be 5 centimeters. The amplitude is going to be half of that, so the amplitude is going to be 2.5 centimeters, and that's just worth 1 mark, just for you to be able to read it off the graph. The frequency. So I know that it takes 16 seconds to go one cycle and half a cycle. So 1.5 cycles equals 16 seconds. Okay, so 1 cycle is, so 16 divided by 1.5, so 16 divided by 1.5 is 10.66 seconds. Okay, so 16 divided by 1.5, yep, 10.66. And then frequency is 1 over the time period, so that's going to be 1 divided by 10.66, so 1 divided by that. I end up with an answer of 0.094 hertz. Oops, that's like a 7, that should be hertz. Just going to check the answers in this one, I always do. Yep, 0.094, that's what they're after here. Okay, so there's 1 mark available for working out that it's 1.5 cycles, so working out the time period, and then 1 mark for using the formula there. Okay, the angular velocity. So the angular velocity is, again, a term that we use in circular motion, but it's to do with the fact that this is a cyclical motion. So angular velocity, when we talk about moving in a circle, it kind of makes sense because you're sweeping at an angle. But if you imagine that is a cycle instead, so 2 pi is 1 cycle, the angular velocity is exactly this kind of, we're using that terminology here to know how far is it through, so how fast does it move through its cycle. So I've got 2 pi f, so it's going to be 2 pi times by this 0.094. So times by 2 times by pi is going to be 0.59, so 0.59 rads per second. So I know that it's going to go for about 0.6 of a radian of its cycle every second. Okay, and that's what it kind of means here. So it's just trying to get your head around why are you using a circular motion thing for this. What you're actually using it for is your angular velocity. In this case for SHM is how fast is it going to move through its cycle. So every second through its cycle, which is a total of 2 pi radians, I'm going to move between about 0.6 of it. So there's 1 mark for using this formula and 1 mark for the answer there. So the maximum speed of the body, so Vmax equals omega times by the amplitude. So that's going to be 0.59 times by 0.025. So everything has to be in meters per sec, meters, etc. So that's going to be times by 0.025, so my amplitude, and I get an answer of 0.015 meters per second. So that's the distance it travels every second. Okay. And lastly, the maximum acceleration of the body. So A max, or acceleration, equals omega squared times by the displacement. And that comes back to our idea that it's proportional. And then the maximum displacement you get, of course, is the amplitude. So the acceleration is omega squared A. So I'm going to have 0.59 squared times by 0.025. So times by 0.59 again, and I end up with 8.7 times 10 to the minus 3 meters per second squared. And again, these are all worth 2 marks. There's one for the formulae and one for the answer, one for the formulae and one for the answer. Okay, so again, these are quite nice, simple SHM questions, just using the formula and just getting your head around them. Okay, so I'm going to talk about this one. This was actually quite interesting because it's all to do with these two, all to do with like spring systems and things like that. And these are slightly different. So this is a body in a diagram, has a time period of 2 seconds, and it has a mass of 60. And it's a vertical system, and it goes back and forth, back and forth. So calculate what it says here. Is it asks you to calculate the amplitude. So it tells you it goes between these points shown, and the total distance it goes through is 20 centimetres. Calculate the amplitude. So of course the amplitude is from the equilibrium point. So if it goes through a total of 20 centimetres, if it's an SHM, the amplitude of either side of the equilibrium point would be the same. So if it's going to be 20 centimetres, it'll be divide that by 2. So it's going to be 10 centimetres, which is equal to 0.1 metres. And that's why it's only worth 1 mark. It's a very simple sort of question that's just getting you to read the object. Calculate the maximum acceleration. Okay, so this one's a little harder. So I know from the last question, whoops, let's just get out of this red pen, that A max is omega squared times by the amplitude. But, of course, I have the amplitude now, but I need to find out what omega squared is. So remember, omega is 2 pi f, or 2 pi over t. So in this case, it's going to be 2 pi over 2, because it's told me that the period of this motion is 2 seconds. So I know that omega is going to be pi. So therefore, I've got omega max equals pi squared times by 0.1. So pi squared times by 0.1, and I get an answer of 0.99 squared. Okay, so this is actually quite a mean question because you can sometimes see students get confused because they go, what have I got here? But much like I've told you before with circular motion, if you do get a time period, you should really see that time period and go, cool, I can do omega equals 2 pi over t, and then work out that what omega is here. And that's the kind of thing that is just a little hint for you. So the maximum speed, of course, is V max equals omega times by A. So it's going to be pi times by 0.1. So it's going to be pi times by 0.1, and that's going to be 0.314. There. Now, force constant on each string. Now, I want to just kind of make you aware of this one because it's a little tougher, because some students may be tempted to just go t equals 2 pi square root m over k and solve it. But you can't do that here. And the reason being is because actually what's happening, if you go out to the picture, is you've got springs working together. So one's extending and one's contracting. The t equals 2 pi root m over k assumed there was one spring acting, and that spring was the driving force of that object. What you actually have now is you have 2 springs acting, And what that means is that you're a little bit, you can't kind of use the data that you've got to use t equals 2 pi root m over k. Okay, so let me just put this down here. So you can't use, because there are 2 springs. And that can throw a few students. They'll do this and they'll get an answer that's actually going to be double what they think it is here. So one of the things that you do know, so this is force constant. It's another term for spring constant that you sometimes see. You do know the spring constant again, it's force equals kx. Okay, and the maximum force that you're going to have on the object is going to be at the maximum displacement. So you have F max equals K times by this amplitude here. All right, so you know that F max is that. And as with orthos, you're going to F max also, because it's linear motion, is M A max. And you've already worked out the maximum acceleration up here. So you know that F max equals M times by omega squared A, and that is also going to equals Ka. The A's cancel, you don't need the amplitude at all. This is why, because it means that all of these are constant, which means the spring constant is magically constant, which is really, really useful. Okay, so the mass of this object is 60 grams, I believe. Yep, 60 grams. So I've got 60 divided by 1,000, because it has to be in kilos. Equal, times by omega squared. So this is times by 0.99. And that's going to equal my spring constant there. So I've got 60 divided by 1,000 times here by, oh no, I do apologise. I've actually I've just realised the question. It actually the object is going to extend by 10. Just want to make sure. Okay, so here, this question here, I've kind of taken a slightly different route. So I'm just going to rub this out a little bit. And it's actually to do with how I've related the force here. Okay, so I know in total, I do apologise, this F max here, so the maximum force that's in my system at any point in time is 60 over 1,000, so that's it in grams. Kilograms, sorry. Times by 0.99. Okay, so that was my acceleration I got. So 60 divided by 1,000, times by 0.99, and you get an answer of 0.06. Okay. Oops. So this is actually quite useful. It's something that I didn't, I kind of like glossed over. I kind of mentioned, but then when I was actually doing the maths, I do apologise, I kind of made it wrong. That the maximum force here is actually shared between these 2 springs, which is why, again, you can't use this formula, because the actual force is going to be spread between these 2 springs. The maximum force that is felt by the tension of this one and the compression of this one. So each of these springs in total, so each spring in total, so the total force equals 0.06 newtons. And that is shared between 2 springs. So 2 springs feel that. So 1 spring equals 0.03 newtons. And then I can, of course, use F equals Kx. And of course, in this case, the maximum extension is going to be the amplitude, so 0.03 newtons here. So I've got K equals K times by 0.1 equals 0.03. Okay, which means that my K is going to be 0.03 over 0.1, which is going to be 0.3 newtons per meter. And so this is actually one of the tricks, and I actually partly fell for it, even though I started that you can't use this formula here because it's got two springs. And then what I tried to do was, weirdly enough, try to derive that formula again, and I should not have done that. What I should have done is gone, cool, I know what the maximum force was at any point. So the maximum force on this ball at any one time, the maximum force at any one time is going to be 0.06 newtons. And that 0.06 newtons is given not only by one string extending, but the other string contracting. And that is why, the total force is that for two springs. So one spring is going to be that there. So K is 0.3 newtons. It is a very mean question. And as you can see, I fell down for it as well. So you can't use that at all. You got 1 mark for doing this, 1 mark for working out that, and 1 mark here for getting the answer here. If I actually go to the mark scheme itself, the exam board will give you 2 marks just for kind of cottoning on that you understand that the maximum force is at the maximum displacement. So if you worked out what the maximum force was, so 60 millinewtons, and then F equals Kx, you would get 2 marks. So even though I was getting it, I went slightly down the wrong route. Even though that route, I would have still got 2 out of 3 marks. So it's useful for you to be aware of that one. Okay, this one. This is again another interesting question here. So the spherical object shown in the diagram is known to perform simple harmonic motion. Between A and B, the object appears to be stationary when we shine a 21 Hertz light on it and a 28 Hertz stroboscope on it. So no frequencies in between. The object is known to have an integer value of it in frequency. So what it means is that when I shine my stroboscope on it, it looks like it's stationary, so it hasn't moved at all between 21 and 28, which means that there must be something common about those two, which means that's the frequency of the object. So if it was 28 Hertz, for example, if this object had a frequency of 28 Hertz, it wouldn't have frozen at the 21, it would be somewhere in between. This means that there must be a common value between 21 and 28, and the only value that is common between 21 and 28 is 7. So the idea is that the object has a frequency of 7 Hertz, so it's going to move 7 times every second. So when I have here, it goes 1, 2, 3, 4, 5, 6, 7 every second. When I shine a light on it that's moving, that's flashing at 21 Hertz, this one would have gone through 3 cycles, and the other one, it would have gone through 4 cycles, but it still would have been pictured at the same position. So since 21 and 28 have a common value of 7, this must be the frequency. There are no other common values between them. It's just 7 Hertz. So you now know the frequency of this object is 7 Hertz, which is really useful to know. So the maximum speed of the object, Vmax, I'm going to keep using this formula, is omega times by A. Omega is going to be 2 pi over, 2 pi f on this one, it's much easier, times by the frequency, so that's 2 pi times by 7. So 7 times 2 times pi, that's going to be 14 pi, so 44. So that's going to be 44 rads per second. And so Vmax is going to be, in this case, 44 times by my amplitude. So this is my oscillation here. My maximum amplitude is 10 centimeters. So 0.1 there. So 44 times by 0.1, and I end up with a maximum speed of 4.4 meters per second. Okay. So again, this is a bit of a mean question, of course, but it's just one of those things that's really useful to know what this kind of question is asking. So this one here, this idea of if you're flashing at 21 hertz. So you're flushing it 21 times every second. And you know that this object moves 3 times every second as a frequency of 7 hertz. It doesn't look like it's moving, which means it must have a common denominator. It's now asking for the acceleration at position x. So I know that a equals omega squared x. So omega squared, so that's 44 squared times by the displacement at position x, which is 0.04. Okay, so 44 squared times by 0.04, that's going to be a value of 77.44, and that's towards the centre. So that would be right. So what's actually happening is this will, at this point here, it will have an acceleration this way towards the centre of the object because the displacement is outwards. So it's always trying to go positive. And now it wants the speed at y. Whoops, gone too far up. So it wants the speed at position y. So this is actually using a slightly different formula, which is actually on your data sheet. Okay. So on your data sheet, you are given, if I just grab one out here, you are given the formula. SHM. Wait a few seconds. Where's the formula? Let me just grab it for you. I'll just grab it off the internet, that's fine. So AQA data sheet. Very specific formula that you can use. Physics data booklet. So the formula that I'm after is in SHM, and it's V equals plus or minus. So you can use this one here. So V equals plus or minus omega, the square root of x squared minus a squared? A squared minus x squared. A squared minus x squared. Okay, so this is the speed at y. This is a formula that you can use. Okay, you're also allowed to use, if you do know it, you can use V equals omega A sine omega t. That's another one you could also use, but you of course need to find time for that one. But I'm going to be using the one that's in your data sheet that's readily available for you that you can use. So here I've got omega, so I've got equals plus or minus omega. So omega here is 44. Times by the square root of the, so what we got here, we've got the amplitude, which is going to be 0.1 squared, whoopsie daisy, 1 squared minus 0.09 squared, so 0.1 squared minus 0.09 squared, that's going to be plus or minus 44 times the square root of 1.9 times 10 to the minus 3, square root that, and times it by 44, and I end up with a speed of 1.92 meters per second there. Just grab the mark scheme. 1.9. Okay, so that is one of the things that you can do here is that the speed at y, you can use this formula here, and it's normally the one that's normally forgotten about by students that you can actually use, and they get into a bit of a pickle and they want to use the sign, but this is actually a really useful one that you can use. If you think about it, what would happen here if you had your maximum acceleration, a squared minus a squared, which is 0, and it all goes a bit squiffy, so basically we use v equals a there with acceleration, of course, we've got here. All right. So just run you through the marks of this one. It's just one for the formula again and one for the answer of 1.92. 1 mark for this, 1 mark for this. It seems like a lot of work to do for that one, which is frustrating. But there we go. There's some SHM questions just using some of the basic formulae. So I've been using the A equals omega squared x, V max equals omega squared A, omega A, and I've been using this really random one, which is quite rare to see, but it does come up. So just remember, it is in your data sheet. So this is in your data sheet. So you just know it's there, so you can use it at any random point. Okay then guys, so that's some basic exam questions for SHM. Hopefully that will help. And I'll see you guys soon. Take care.